Hello, my name is Alex Borges. I'm a PhD student in computer science from Federal University of Pelotas. I'm a research member of the Video Technology Research Group, VTech, and I come here in EUSIPCO 2020 to present my paper, named Fast VP9 to F1 Transcode based on block partition inheritance.
A consortium called Alliance for Wikimedia was founded in 2015 to provide a new video encoder free of royalties, based on three open-source video encoders, VP9, Dala, and Tor. In 2018, the EVO1 was launched. Since the EVO1 launches, many companies have developed a video encoder and decoder based on EVO1 format, but only one is considered the EVO1 reference software, the LibOM, developed and maintained by the EU Media. It's possible to find many papers published comparing EVO1 against other video coding formats from 2016 until nowadays, especially EVO1 against VP9. In this slide, I select only 4 of these papers. On average, the LibOM codec has 19% better coding efficiency against the VP9 reference software, libvpx. However, LibOM needs more than 94 times of execution time than libvpx. This is an important thing to note. Focusing on VP9 owned by Google and on EVO1 owned by EU Media, where Google is one of the founders, we propose a VP9 to EVO1 video transcoding, aiming to offer a better coding efficiency from video sharing platforms as YouTube, and indirectly for the final user, that they will have less bandwidth consumed to watch their videos. But what is transcoding? Video transcoding is a process that converts a bitstream saved in a format or configuration to other video format or configurations. In our case, a heterogeneous video transcoding decodes a VP9 bitstream to re-encode the raw video in an AV1 video bitstream. An important fact needs to say, there is no work presenting a fast VP9 to AV1 video transcoding in the literature. In this paper, we present the first video transcoding from VP9 to EVO1, making use of partition block informations. Well, how do you do that? It's simple. Both VP9 and EVO1 formats are block-based hybrid video coding, so both formats divide a frame into smaller parts, called superblock. In VP9, the superblock has a size of 64 by 64 pixels, and in EV1, the superblock grows to 128 by 128 pixels. Each superblock is subdivided into a tree of blocks that can assume many shapes and size. The superblock structure is composed of blocks. We normally see this structure as a block arrangement, but internally this structure assumes a tree structure like that. All blocks and shapes are combined into 4 types of partitioning inside the VP9. This partitioning can assume non-vertical or horizontal types. Also, have a 4th type called split, which means that this block is subdivided into 4 new and independent superblocks with half size. Every time a split is selected, the depth level of the partition tree is increased. If one expands this type from 4 to 10, assuming new combinations. To verify the correlation, we get the information from libvpx and libOM decoder, as is shown here. It got the depth level and partition type for every 4x4 version of the video. We perform this statistical analysis for every recommended C key, 20, 32, 43, and 55. In this slide, I show you the statistical analysis of partition types correlations for C key equal 20. Columns represent all choice made by VP9, and lines represent the choice made by EV1. If we highlight only the VP9 32 by 32 non-decision, we get this plot. When LivePX chose 32 by 32 non, in more than 30% of the time, the LibOM also chose the same partition type. This fact is also true when LivePX chose the 16 by 16 horizontal, with less precision. Just mapping the partition type observed in the LivePX to be applied into LibOM is not efficient, because we should ignore other 78% of choice probabilities. What we propose is LibOM will test only the most probable partition type for every EV1 square block size. That is, for 128 by 128, the choice must be none, with less than 1% of probability. For 64 by 64, also is chosen none. For 32 by 32, horizontal. For 16 by 16, horizontal, as expected. For 8 by 8, none. So, instead of only 21.5% mapping accuracy, it is proposed to obtain an accuracy of 49.72%. Of course, this precision is only for VP9 16 by 16 horizontal. Considering all block partition and all C-key, we can achieve 60% precision. So, we can show you our fast transcoding, and this is the summarization of our fast LibOM algorithm. After starting the superblock coding, LibOM will load the VPX information from a region of the superblock. Next, LibOM will verify if the actual block size being processed is smaller than 8 by 8. In a positive case, LibOM stops this sub-tree processing. In other case, LibOM looks at the previous table to obtain the correct partition type. So, according to the mode selected, three possibilities of flow can be executed. After this processing, we look if we will be choosing to select mode or split. In case of split, 4 new subtrees will be created and the flow repeats. Either stop the process. To perform the experiment and to put our solution to the test, we use these 20 video samples. We use the following configuration to LivePX and LibOM. Here, we show the average obtained by the execution of all video sequences. For every sequence was obtained the video rate, time saving, TS, and the ratio between video rate and TS. It is possible to observe that our solution accelerates LibOM by 28%. To provide this acceleration, our fast LibOM lost only 4.3% of coding efficiency. Our fast LibOM solution can provide good results in Group B videos, while for screen content video of 80x1080 present the worst result. But now it is important to show the compression efficiency against the LivePX, aiming to justify that our fast transcoding is still better than keeping videos encoded in VP9. Well, here we have the comparisons. Look at the coding efficiency obtained by the original LibOM against the LivePX. Reduced more than 21% of bit rate. Remember, the average of papers comparing the EV1 with VP9 shows 19% of bit rate in favor of EV1. So, this result is compatible with the average. However, our fast LibOM encoder can obtain more than 18% of bit rate against the LivePX. That is still compatible with the average presented by the beginning of this presentation. and our solution only achieved 3.2% less coding efficiency than the original solution when compared to the VP9 encoder. In this slide, I show you the difference in coding efficiency provided by the original LibOM or FastLibOM and by libpx. This data is based on the best case of FastLibOM against the original LibOM. As it presents, both LibOM solutions have a superimposed curve because the bit rate is low, and even so, it was possible to obtain 33% of time saving. Comparing our FastLibOM with libpx, it is possible to see that our proposed solution is 27% more effective at encoding a video than libpx. Even for the worst result presented by the FastLibOM against the original LibOM, where the curves are no longer superimposed, the coding efficiency still is much better than the offered by VP9, achieving a coding efficiency of more than 34%. Okay, what can we conclude from this work? Paper presents the first fast VP9 to EVO1 video transcoder. This transcoding proposes the use of VP9 partition type information as inheritance to speed up the EVO1 encoding. The solution can provide an average time reduction of 28% of LibOM. This acceleration has a cost of an average loss of 4.3% in compression efficiency. Despite that, transcoding from VP9 to EVO1 is still beneficial, since the format conversion leads to coding efficiency increase of 18.6%.
This is my work. Thank you for watching. Do you have any question?